thank you to the organizers for the kind invitation. Can you hear me with okay, good, very good, wonderful. Okay, so I changed a little bit the title of my talk. I was going to talk about energy and also vorticity, and I decided to concentrate only on energy here. Okay, so let me start by acknowledging my collaborators. So Alexei Sheskidov from University of Illinois, Chicago, Milton Lopes Filho, he's here in the audience from Federal do Rio de Janeiro, Roman Schvitkoy, also from University of Illinois, Chicago. Okay, so let me go through very fast the beginning because this is well known to this audience. So the equations modeling incompressible unforced fluid flow is just ut plus u grad u is minus gradient of pressure plus nu Laplacian u. Divergence of u is 0 is incompressibility, and nu equals 0 corresponds to the Euler equations, and nu greater than 0 to the Navier-Stokes. Okay, so for smooth solutions, the whole story starts with the following trivial calculation. ddt of 1/2 of the integral of u squared is minus the integral of u grad u minus u grad pressure plus nu u times Laplacian of u. And that can be written in this nice divergence form, exact derivative minus nu times the dissipation gradient of u squared. And since you have, if you have no boundaries, then the terms which are exact derivatives just integrate to 0. So this just gives you minus nu times the integral of gradient of u squared. So for smooth inviscid flows, in the case where viscosity is 0, they just conserve kinetic energy exactly, okay? As long as you're smooth. And the whole point of my talk is what about this goes through for weak solutions, for irregular solutions. Now, anomalous dissipation is a cornerstone of turbulence theory. So, in other words, inviscid fluid flows which do not conserve kinetic energy. Okay, so turbulence requires anomalous dissipation, which requires irregular flows, non-smooth flows, because for smooth flows you have conservation of energy. In 1949, Lars Ansager conjectured that anomalous dissipation could happen for inviscid fluid flows with less than a third derivative, third regularity in some sense, and that inviscid flows with more than a third derivative do conserve kinetic energy. And research on the Ansager conjecture developed along two different fronts, flexibility and rigidity. Okay, so let me give you a very brief history of this problem, which has been, quote, completely solved, unquote. So on the flexibility side, the research led to the wild solutions, which started in a paper from 1993 by Vladimir Scheffer, which was rather unreadable, followed by a paper by Sasha Schnirelman in 1995, much more readable. So these were papers in which they constructed inviscid solutions of the Euler equation, inviscid weak solutions of the Euler equations, which were compactly supported in space and time. And they were only, the problem is they were not in the physical space, they were only L2 in time, L2 in space. So they were not in the physical space, L infinity, L2. Then this was followed by the work, the pioneering work, breakthrough work, in fact, of Camilo Delelis and Laszlo Zaglihidi from 2009, where they showed, again, the existence of compactly supported in space and time weak solutions of Euler equations that were L infinity L2, and they were even more. They were L infinity period. Okay, then this was followed by a whole bunch of papers, and basically you from one day to the next, you go to archive and there's a new paper in which they started to lower actually to increase the regularity of their non-unique wild solutions. So the next major work was by Phil Isett in 2013, where he produced a C0 1/5 solutions. And then in 2016, Tristan Bickmaster joined the group as a student of Delalis Zekelihidi, and he got L1, and they got L1 in time, C1/3 in space. Then all of these were three-dimensional constructions. And then in 2013, there was the first truly two-dimensional construction by Antoine Chouffroux, C1/10 in space and time. And then finally, I set with the complete proof of the Alzhauer conjecture, where he produced solutions which were C0 1/3 minus epsilon, compactly supported in space, in time, periodic. Sorry. Okay, so again, this continued, the story continues. In 2019, the Big Buckmaster and Nicole, thank you. I have some water, thank you. Okay. They produced viscous solutions, viscous wild solutions. And they showed that these converge to an inviscid limit with anomalous dissipation. This is an eminently three-dimensional construction which cannot be reproduced in 2D. Okay, so this is not entirely related to the anomalous dissipation, but I want to mention the construction by Brouet and Colombo from last year with non-uniqueness in L1 infinity, vorticity in L1 infinity. And finally, the non-uniqueness of Leray-Hopf solutions due to Albritton, Brouet, and Colombo from early this year, late last year, which is not a convex integration result. Okay. On the other side, the rigidity. Okay. The first work is due to Frisch and Sulem from 1975, where they proved that if the velocity is in L infinity h5/6, then kinetic energy is conserved. So this is for Euler. Then two papers from 1994, Inc. and the state-of-the-art Constantin E. and Titi, showed basically that if the solution, the Euler solution is L3 in time, B1/3 plus epsilon 3 infinity, these are Bazov spaces, this is really the correct regularity in a sense, then the energy is conserved. And you can lower this 1/3 plus epsilon to 1/3 by looking at B1/3 3C0, i.e. the Littlewood-Paley components vanish at infinity. So L3 in time, B1/3 3C0. is a result due to Sheskinov, Konstantin, Friedlander, and Schvidtkoy. Okay, and their result is 3 dimensions and 2 dimensions. Okay, so in 2000, Duchamp and Robert proved a result that's only valid in 2 dimensions. If the initial vorticity is an LP for P larger than 3/2, then conservation of energy happens. No anomalous dissipation. And you can reach P equals 3/2 through the work of Sheskinov, Konstantin, Friedlander, and Schvidtkoy, because, well, we'll see later, the velocity is W1 3/2, and that's included in L3 B1/3 3C0. All of these results involve studying optimal conditions for the energy flux to vanish. Okay. Now I want to concentrate on 2-dimensional flows. So here we are, the Euler equations in 2 dimensions, and we're going to be looking on the torus for simplicity. Okay. So we're interested in weak solutions of the Euler equations for which the vorticity is some kind of pth power integral, LP, for some p greater or equal to 1. So since the vorticity in 2D is just transported by the flow, the velocity u, which is divergence free, the LP bounds are preserved by the evolution, and so this is a problem that makes perfectly good sense. The wild solutions do not have any control on integrability of vorticity. Even the L1 infinity wild solutions constructed by Drouet and Colombo, because their L1 infinity is not a subset of L1. Okay, so here's a definition of weak solution that we deal with. Just a moment. Okay, so if you just multiply your equations by the test vector field and throw derivatives onto the test vector field, you get the identity displayed here, and the divergence-free condition has to be satisfied in the sense of distributions. Now, existence of such weak solutions is known for all values of p greater or equal to 1, and wow. So p greater than 1 was work by Deperna and Maida from the late 80s. P equal 1 is work by Vecchi and Wu, and it's also sort of implied in the work of Delors from 1990. Uniqueness is open except at either L infinity or some nearby spaces. And I'll just refer to a weak solution as being conservative if the L2 energy is, L2 normal velocity is conserved. So here's our baseline result. It's the p equal 3/2 result. And I'm going to give you an elementary proof. Okay, so this is contained in the work of Sheskinal, Friedlander, Konstantin Friedlander, and Schvidtkoi, but I'm going to give you a proof that is entirely elementary. And furthermore, the local energy balance law also holds. Okay, so here's the vorticity, which I'm assuming is bounded in L3/2, and then kinetic energy is conserved, and the local energy balance law holds. Okay, so what one does is to mollify and the structure of the proof is very much all about what all of these proofs are. So basically, you mollify the PDE, and you look and you throw the problematic terms into the commutator, this Reynolds stress R epsilon, and then you just now you have a smooth solution, but with this R epsilon here. Here we go. Okay, and when epsilon goes to 0, you have the convergence of all these terms to the right object. Okay, the crucial thing is this last one. C u dot r vanishes strongly in L infinity L1. A and B are subcritical for vorticity in L3/2, and it's the last one which requires vorticity to be in L3/2. Okay. This proof uses the fact, so here's the outline of the proof. If the vorticity is in L3/2, the velocity is in W1 3/2. That embeds by the Sobolev embedding theorem into L6, and then all of the terms that you need are actually in L1. You're going to have u in L6, u in L6, so u squared is in L3, and that's the dual to L3/2. That's it. Okay. With Alexei Shchedkinov and Roman Shvidko, we went ahead and produced a divergence-free vector field in B1/3 infinity, intersect W1P for any P less than 3/2, for which the energy flux does not vanish. So this represents the energy flux at the through a dyadic shell of frequency 1/2 to the Q, sorry. And as Q goes to infinity, you expect this to vanish if you have energy conservation. Okay, so this example here is not a dynamical example. So this is an example which simply illustrates that the method is optimal. Okay? It's an example which just tells you about the technique we're using. All right, so at this point we pose ourselves the question, is it possible that there's an Euler solution which has some integrability of vorticity and is still not conservative? Krashen 2D turbulence theory tells you that you expect a forward entropy cascade, which implies some kind of regularizing effect in 2D. And so it suggests that there may be some dynamical mechanism which avoids anomalous dissipation in 2 dimensions. So then we started looking at vanishing viscosity solutions. And we introduced the notion of physically realizable weak solutions, which are simply those weak solutions of Euler which are some kind of weak limit of vanishing viscosity. Okay? The actual family which realizes this is called a physical realization. And with this, we managed to prove the following theorem. And this is a fairly old theorem at this stage. If you have a physically realizable weak solution for which the vorticity is in LP for any P greater than 1, then if you have a physical realization for which the vorticities are bounded in LP, this is something that you can choose, then the Euler solution will conserve kinetic energy. And I want to note that P less than 3/2 by the previous argument is ensemble supercritical. Okay, so I'm going to give you a brief proof because this is a pretty simple result. Suppose you have an initial vorticity, which is an LP. Take P less than 2, otherwise the result is trivial. And if U is physically realizable, you can choose a physical realization. The vorticity equation, since you have no boundary here, it's just ddt of omega nu plus u nu, grad omega nu is nu Laplacian omega nu. And then you just, you can write what happens with the L2 norm, squared of omega nu. So it's given, ddt is given by minus twice nu times the gradient of omega nu squared in L2. You can just use Gallardo-Nirenberg, which gives you that the L2 norm of the vorticity is bounded by the L2 norm of the gradient times the LP norm of omega. And there are some powers here, 1 minus P/2 and P/2. So since you're interested in minus 2 nu gradient of omega nu squared, you can invert this relation. And then you can go back to the vorticity equation and get an a priori estimate on the LP norm of the vorticity in terms of the initial LP norm, which you know it's bounded because of the existence of the physical realization. So you input this back into your equation for the time derivative of the LP norm, L2 norm of omega nu squared, and you get this estimate here, which you can rewrite as this differential inequality. y prime is minus twice some constant times nu times y to this 2 over 2 minus p. The critical thing is that this exponent 2 over 2 minus p is greater than 2. Okay, and here's where p being greater than 1 comes in, by the way. If you integrate in time, starting from some positive time delta, then you get this estimate here. And now you can take the limit delta going to 0. Before you couldn't because you do not know what happens with omega naught nu, L2. But here, you have that if, whoops, not even appearing. If omega naught nu L2 is infinite, then since you have a negative exponent here, this is just 0. Otherwise, it is what it is. Okay, then we go back to the energy identity for Navier-Stokes, for 2D Navier-Stokes, which you can rewrite in terms of vorticity. And then we input what we have just learned about the L2 norm of the vorticity and integrate in time, and we get finally this estimate. U nu L2 squared minus U not nu L2 squared less than or equal to 0, and it's greater than or equal to this integral here, which when you integrate, you wind up with, this is no longer working, you wind up with this estimate. Okay, now, what's crucial here is that when nu goes to 0, okay, omega naught nu, whether it is infinite or not in L2 initially, it ends up going to infinity. So if you go back here, you can get rid of the term omega naught nu to this L2 to this negative power. That's just 0. Okay? And you have nu to the power 2 times p minus 1 over p. And that power is positive. So your right-hand side goes to 0 when nu goes to 0. If you started with a physical realization for which the L2 norm was already infinite, the entropy, initial entropy was already infinite, then you'd even get a rate. Okay. Either way, when p is greater than 1, the right-hand side vanishes as nu goes to 0, and you've just proved that the energy at time t and approaches the energy at time 0 as nu vanishes. Now, Dupert and Maida, as part of their proof of existence in LP for p larger than 1, they proved the following non-concentration result, that for each time, uniformly in time, in fact, the L2 norm of the viscous flow approaches the L2 norm of the inviscid flow. And you put that together with our assumption of strong convergence of initial data, and you conclude the proof. This concludes the proof. With this, you have just shown that the L2 norm at time t of the inviscid solution is equal to the L2 norm of the initial inviscid data. Okay, let me make some observations. First of all, there's some recent work by Samuel and Haller, Sid Mishra and Carlos Perez Pulido, where they obtained, this is very recent work, where they obtained an equivalence criterion. Okay. So here we have a result which says that, okay, the vorticity is an LP, p larger than 1, then you have conservation of energy. But they actually show that the L2 norm is conserved in time if and only if a certain criterion which includes LP vorticity. Their criterion is given in terms of something they call time-dependent structure functions, time average structure functions. Okay, and their condition provides us an immediate proof. So then this result now becomes an immediate corollary of their work, but they don't have any rate. On the other hand, in view of the result, you can extend our result to other conditions on vorticity as well. So for instance, if the vorticity belongs to any rearrangement in invariant space, which is compactly embedded in H-1, then you again have conservation of energy. For instance, all of these Orlik spaces, L log L to the alpha, for any alpha greater than 1/2, are included. All of these Lorentz spaces, L1p, for p less than 2. Okay, but these are different Lorentz spaces from the ones considered by Brouet and Colombo. Okay. The case omega naught in L1, the initial vorticity in L1 is left open. Not only it's left open, but the if and only if criterion says that you're going to have conservation of energy if and only if, for a physically realizable weak solution, if and only if the vorticities converge, and only if you have strong convergence of the velocities. And this is something that we really do not expect if the vorticity is L1. We do not expect to have compactness in L2 for the corresponding velocities. So it's unlikely that we'll be able to establish conservation of energy if the initial vorticity is L1. Okay, yeah, this is just what I'd mentioned about the structure functions. All right. We then went ahead and decided to look at forced flow. Okay. So what I'm reporting now is joint work with Milton. Okay. And instead of energy conservation, we became interested in energy balance. Okay. We sought regularity conditions on the forcing for which you have energy balance. Okay. And this is the motivation for this is because forcing is a natural mechanism to generate turbulence. Okay, we need to adjust the notion of physically realizable solutions to include the forcing. So this forces has to converge weakly, L1 in time, L2 in space. And with this, we have the following theorem. So if I have a physically realizable weak solution with a physical realization, and I have to assume the following extra hypothesis. So the vorticity is again LP for p larger than 1. And the vorticities need to converge strongly in LP. And the curl of the forcing has to be bounded L1 in time, LP in space, L infinity in time, L2 in space. And then use energy balance. These are pretty strong assumptions on the forcing. So this is still unsatisfactory, sort of a first result. Okay, let me give you briefly the proof because it follows the lines of the previous proof, but I need to show you what adaptations we had to make. So we start with our basic estimate for the L2 norm squared of the vorticity, which can be rewritten in this way. So we have the entropy, the DDT norm of the entropy is bounded by minus some constant times viscosity times L2 norm squared to the power 2 over 2 minus p. That term was already present before, plus the extra term, b times L2 norm squared to the 1/2. That's the term that comes from the forcing. And we no longer have managed to get such a nice estimate. To integrate this explicitly and get such a nice estimate for the behavior of the entropy. Instead, we simply show that the dissipation vanishes. Okay? And how's this done? First of all, our energy estimate is this. This is the differential inequality that we have to deal with. So you have this power. So here, one thing is what is playing against each other is you have minus a nu times z to some exponent which is greater than 2. That comes with a negative term, plus b plus something which grows slower. B positive term, z to the square root. Okay, so a and b are independent of nu. Okay, I do not know what's the behavior of the initial data as before. Okay? And this is going to be important. This is going to play a role. But whatever it is, at any positive time, this is going to be finite. Even if it's infinite initially, eventually, for any positive time, it's going to be finite. So we divide the proof in several steps. Step one, we look at the equality for this differential inequality. And we show a ground wall type estimate. So Z is going to be below M. And then we look at the behavior of this M. Okay, now the problem here is that we don't really know what's happening for the initial data, and the coefficients are new dependent also. So the key is to look at the equilibrium for the equation for M, and to notice that phi changes sign just once. Okay, it goes from positive to negative. So what this means is that if you start above the equilibrium, you go towards the equilibrium. If you start below, you again go towards the equilibrium. Okay? And this is going to give you that Z is bounded by the equilibrium if you started below. And if you started above, Z is below M, but M is going to travel towards the equilibrium. So we need to consider three different cases, depending on what's the lim sup when nu goes to 0 of the initial data for Z over this equilibrium. In the first two cases, which are less than 1 or equal to 1, they lead to Z nu is comparable to the equilibrium, and that's good. Okay? Because then you're going to have that nu times the integral of omega L2 squared is bounded by nu times the integral of R nu of the equilibrium, and that vanishes when nu goes to 0. Okay. It's the third case that's complicated, when the lim sup is greater than 1. Then you basically integrate the ODE for M, not explicitly. Okay. and so you're forced to study this function, capital phi nu, and prove that it's strictly decreasing, it has an inverse, and it goes to 0 when R goes to infinity, and it goes to infinity when R goes to the equilibrium. It's only defined if you're above the equilibrium. Okay? With this, you finally arrive at an explicit solution for M, quote, explicit, unquote, which gives you an estimate for Z. Ultimately, gives you an estimate for Z. And then you need to introduce another element here, which is above the equilibrium. And what this R nu double star does is it tells you, okay, if you're above this guy, then you're really behaving like this. Then the Z to the power square root, to the power 1/2, plays virtually no role. So your flux is really dominated by R to the alpha for alpha greater than 2. Okay, and now you can finally estimate your dissipation term in terms of this R nu double star. Okay. And this is enough to conclude. Once you have this estimate, that's enough. So the key points were an adapted ground wall using the fact that your flux is concave. And you don't need only estimates, but you actually needed precise asymptotics with respect to nu. Okay, so here are some conclusions. The Onsager scaling, as we have seen, is not the last word on inviscid dissipation. And in 2D, you do have a dynamical mechanism that avoids anomalous dissipation. Our solution is L infinity in time W1P in space, our velocity field for P greater than 1. What we've seen is that in this case, 2D physically realizable weak solutions do conserve energy. And therefore, they're not attainable through convex integration techniques. This supports some kind of selection criteria. The selection criteria, the idea of this, of using physically realizable solutions as selection criteria, is present in the work of Claude Bardot, Dries Titi, and Emil Wiedemann from 2012, where they study shear flows in 3D. And they show that the vanishing viscosity limit selects one of the weak solutions. Another instance is symmetry breaking, which is also avoided by physically realizable weak solutions. And this was something that we studied with, Milton and I studied with Claude, Dries, and Dong Xuan back in 2013. Again, showed that symmetry selects one. In the presence of symmetry, vanishing viscosity selects only one of the weak solutions. Okay, this work on avoiding anomalous dissipation has been extended to vortex blob method approximation. So not only vanishing viscosity, but also vortex blob avoids anomalous dissipation in this case. And you have local energy balance if you're an LP for any P greater or equal to 6/5. This is work from 2 years ago by Siampa, Kripa, and Spiri. It's also been extended to the axisymmetric case by Camilla Nobili and Christian Seiss in a paper published this year. I think it's earlier work, but it was published this year. They showed that if the initial vorticity is non-negative and first moment is integrable, and if this axisymmetric vorticity is an LP for P larger than 3/2, then you have conservation of energy. P greater than 3/2 is somewhat unsatisfactory, as that 6/5 should be the right exponent. Okay, what about the case P equals 1? As I mentioned, not only there are no tools, but the result is kind of unexpected. And this is annoying because there's a discrepancy with respect to the state of the art for the conservation of vorticity norms, of LP norms of vorticity. We do know that one norm is conserved. So if instead we look at a less ambitious problem, consider L1 vorticity, U physically realizable, and ask ourselves simply whether it can be attained as a convex integration solution. And this is work in progress. And finally, we would really like to have an equivalence criterion a la Landhaler, Mishra, and Pares Pulido in the case with forcing. We'd like to weaken the hypothesis on our forcings. And this is also work in progress. Okay, with that I close. Thank you.
So, are there any questions in the audience? So first, Emil.
Thank you, Helena. So you showed us your nice proof that viscosity limits always conserve energy. Now, viscosity limits are a special case of renormalized solutions. So yes, that raises the questions whether renormalized solutions also would always conserve energy, which I would kind of believe, but I don't know a proof. So do you know anything about this?
Okay, so this is related, I guess, to the connection. How much information can you transfer from vorticity to the velocity formulation? Okay, and that's what, we're missing a step when the vorticity is L1. We just don't know what to do. I mean, the Delors formulation could provide some clues, but we don't know.
Okay, thanks.
There was another question, I think. Yeah.
Hi, so thank you for the nice talk. I mean, actually, it's very much related to the previous question.
I can't hear you.
Is it? Oh, okay, sorry. It's very much related to the previous question. So, exactly, like, I mean, in the case P is smaller than 3/2, like where you have this sort of static counterexample, but which implies that your techniques based on commutators do not work, but you cannot fully settle whether conservation holds or not. Is there any chance to do this in a two-step way? So like first establishing that once you have regularity, these solutions are actually renormalized solutions in the sense of Di-Perna-Lyon, and then based on that information try to like get better conclusions like conservation or other physical properties of these solutions.
So P less than 3/2, they are a normalized solution. We already know that.
But what I'm asking, I mean, if you try to establish conservation on energy based on purely regularity criteria, like saying you have a weak solution whose vorticity is L infinity in time, LP, P smaller than 3/2. Can you like first say, okay, actually from this information I can deduce that this is a renormalized solution, and then from this try to infer conservation on energy?
I guess the answer is I don't know.
Okay.
I don't know.
Thanks.
Okay. Other questions?
Well, thank you very much for this nice talk. I would like to ask you more a philosophical question about, you mentioned the wild solutions which are physically realizable. And well, coming more from the numerical point of view, can you give some comments or some hints? Are there any solutions, wild solutions, which are realizable from a numerical point of view, which we can put into a computer and do computations? There's this recent work by Kavlish and co-workers in JFM for the vortex sheets, where they're trying to compute wild solutions of 2D Euler equations. Is there any hope to do that also numerically?
Again, the answer is I do not know. I know that there is work on illustration of numerical illustration of wild solutions, but
so
I do not know.
Okay, thank you. So in terms of number of scales, there must be a cutoff, and that's maybe a problem. Okay.
These are very good questions. I don't know the answer to.
Okay. Yeah, thank you.
Okay, may I for the last questions? Yes, it's okay. So, concerning the case P equal 1, you have an insight in the if the initial vorticity is positive or not negative, I mean? Does it help?
So, right. Okay, if you have some, I don't think that there's going to be anything to be gained by imposing a sign condition on vorticity.
Okay.
This is what you're asking.
Yeah.
Yeah, I don't think so because, okay, so the equivalence criterion by Lantal et al. Says that the energy is conserved if and only if the viscous vorticities, the viscous velocities converge strongly. And if the celebrated work by Delors, where he takes initial vorticity with a sign, and L1, and you don't even need the sign if you're in L1, right? And we don't know whether for the Delors solutions, we do not know whether the velocity converges strongly in L2. We don't know.
Okay.
I suspect not, but we don't know.
Okay. Okay, thank you. Maybe it's time now to go to the coffee break. So let's thank Helena again.